Good morning. So, in physics, we deal a lot with motion and trying to describe and analyze the motion of objects. So, we're going to come to agreements for how to represent motion in one dimension in this first exploration. And the way we're going to do that is by using a frame of reference. Frame of reference is a coordinate system that can clarify a description of an object's position or motion. So as you're watching this video, please be filling in the blanks, pause, and fill in the blanks as you need it. So let's think about this for a minute. And if I have if I imagine to meet my study partner at the door of the library, one of you starts here from position A, and one of you starts, so your path to the library would be go down the street and take the first left to get to the door of the library. The other person following these directions said go down the street and take the first left, and you would go to town hall instead. How does the starting position affect the directions? So think about that with your partner. Why did one person end up at town hall and the other person following the same directions ended up at the library? Okay. Motion is a change in position relative to something else. It's described within a frame of reference, a system of coordinates with a fixed origin. We might use a Cartesian frame of reference where there's a y-axis and an x-axis, and you can move in a positive or negative direction on either of these axes. Or you might use a cardinal frame of reference, which describes a center point and motion upwards on this plane would be to the north, downwards to the south, and east to the right, and west to the left. So if I want to talk about how something has changed in position, I'm describing its displacement in a frame of reference to describe the change from initial to final position. Where did it start initially, and where did it end up finally? So to do this, we have to discuss the distance, the direction, and the time. Those can all describe the motion, how long it took, which direction it went, and how long did it go. So when we talk about a quantity of any of these things, distance, direction, or time, that both have size and direction, we call those vectors. So sometimes, so to connect this to math a little bit, we're going to do what's called a random walk. And we're going to use a melodic sequencer and coin flips so we can discuss the difference between displacement and distance. So on your choice board, you will notice one of the options is called the random walk coin flip melody in the first row. You can use the online sequencer to model a random walk. Let's go ahead and click on this picture and go to the sequencer link. Now you can select a draw tool, a select tool, and an eraser tool. Let's select the draw tool and start with a note on C4. Just a note there. Wrong one. Let me tuck this one away. Oops. Okay. So it said C3 instead. Okay, I'll change it to C3. C3 or C4, either one's fine. Flip a coin, and for heads, place a note. Let me find my coin. Flip a coin. For heads, place a note one white key above, and for tails, place it one white key below. My first flip was tails, so I'm going to put the next note here. And I'm going to repeat this process 10 times. Tails again. Put it in the eraser. Put it one note below. See how this key is black? We're going to go to the white key. Keep flipping. Heads. So now I go one upwards from where I was before. Keep going in that way for 10 coin flips and see what kind of melody you come up with. So what's going to happen is that after n amount of moves, the note will have traveled a distance of n notes. I said let's do about 10 notes. But it's very unlikely that it will be displaced by 10 notes. The note can be on the starting note after hundreds of moves. So right now, I have traveled a distance of 4 notes, but you'll notice I'm only displaced one note from where I started out. This can actually be used to model several physical and biological processes, such as the motions of gas molecules. I think I closed the wrong one before. Let me go back. Here we go. Now, the velocity of an object is its speed in a particular direction. The average velocity over a time interval is the displacement of the object divided by that time interval. So we'll notice that if this sprinter is photographed at equal time intervals, let's say every picture is 0.2 tenths of a second, and that's the time interval. Draw line segments to indicate the displacement between adjacent and so I'm going to use the foot that's touching the ground, and we can see the displacement between each time interval is changing. There's different lengths. What's happening? Are those lengths getting overall longer? We can see this one's very much longer than how we started out. And what's happening to the sprinter's velocity? Well, we can say right here, his displacement is changing a lot more per unit of time. So we can say his velocity is increasing. We might also show motion on a graph by noticing an object's position over time. So starting from a position of 0, every 2 seconds we can see where its position is on this graph. If I put a straight edge between the points for where t equals 0 and t equals 2, I can calculate the average velocity in that segment. So let's see, I'm not sure how to do straight lines, but I'll try my best. So this would be rise over run. So an easier way would be where it intersects a line, and I would say the rise here is 20 and the run is 4. To reduce this ratio, divide both sides by 4, so it would be equal, I'll just do it right here, which is equal to 5 over 1. If I divide both things by 4. 4 divided by 4 is 1, 4 divided by 20 is 5. Now, determine whether this question asks about an average or instantaneous velocity on page 9. So last thing, we're going to jump over to our HMH book for this lesson. Excuse me for not having this up already. It just makes the video a little longer than I wanted to, but that's okay. I'm trying to make these videos as short as possible. I gotta plan them out. So we should be in our lesson called oh, I didn't make the lesson yet. Oh my gosh. Well, let's just go here instead, and we'll click over to the first lesson. So we're on exploring 1, representing motion. Okay, we talked about all this. Take the time to read all this. We're going to do this lab here. Changing position. Okay. So average velocity or instantaneous. How fast must you bike to get there in half an hour? We probably want to know how fast should your average velocity be to get there in half an hour. What is the fastest you can run? At the fastest point of your run, let's measure your instantaneous velocity. What's the minimum speed for takeoff? So we'd want to know what's the slowest you can go in your plane for your tires to leave the ground. At that moment, it would be instantaneous. How fast did he run the first 5 miles? So over this huge distance, what was the average velocity? Let's see. Okay. So instantaneous would be at a particular moment, how fast, whereas average velocity would be over an interval of what time? After you've done your notes, let's go up to the front of the room and do an exit slip. Thank you.